Okay, let's take a look at a couple of curved arrows before we call it a day, and then we'll take a look at some more tomorrow. So these are just problems I took right out of Klein, and the reason why I put these in here is because I don't want you to waste all your time drawing the structure. We just want to get to the good part, drawing the curved arrow. So it says draw the curved arrows for each step of the following mechanism. So we have hydroxide here that's reacting with this big old molecule here, and you can see that the hydroxide ends up, if I highlight this carbon, let's say in green, or sorry, in red, you can see the hydroxide ends up there, okay? So if we were to draw the curved arrows, what I'm going to do is I'm first going to put in the curved, or sorry, the lone pairs on the hydroxide, 1, 2, 3, 4, 5, 6. And so the hydroxide is not going to act as a base, but it's going to act as a nucleophile, and it's going to attack this carbon here. But then if I was to just stop there, that would be wrong, because then this carbon would have, look, 1, 2, 3, 4, 5 bonds. That's impossible. And so you can see that there's no double bond here anymore. Those electrons move down here. There's no double bond here anymore. Or sorry, you can see that those electrons, there's no double bond here anymore is what I should have said. So these electrons are going to go down here, form the double bond to the nitrogen. And then lastly, we're going to break this pi bond and put a pair of electrons out here, okay? So initially this oxygen has 2 lone pairs, but then it ends up with 1, 2, 3, 4, 5, 6, so 3 lone pairs. So there you go. I could have put in all my lone pairs to start with. I left them out. But anyhow, you get the idea. So this would be categorized as a, could anybody tell me what I call this? A nucleophilic attack, proton transfer, loss of leaving group, or a rearrangement? This particular one. Yeah, exactly. Thanks, Aaron. It's a nucleophilic attack. Yes. Okay. The next one, you can see you're losing something. Whenever you see this negative sign at the beginning, that means it's going away, right? And you can see that you have this whole piece here, right, that you lose, and then it's gone from the molecule. So this must be the loss of a leaving group. And so we can see that, excuse me, in order to lose this leaving group, right, we're going to have to form a double bond here. Let me use my red pen. We're going to have to form a double bond here, put this double bond back, put this double bond back, and then break the bond between the aromatic ring and the oxygen that is attached to the sulfur. So it's a collection of 4 curved arrows to lose that leaving group. Then the last one is kind of annoying because they didn't draw this bond explicitly. You actually need that bond. So I'm going to redraw this molecule. So I'll redraw it like this. Here's my nitro group. Here's my alcohol. And so the last step is going to be a proton transfer, where the hydroxide now is not functioning as a nucleophile, but as a base. So it's going to pick up this proton, and you're going to end up with we call that a phenoxide, this thing here. So 1, 2, 3, 4, 5, 6, so 3 lone pairs like that. So we have a nucleophilic attack, a loss of leaving group, and then a proton transfer at the end. All right, for 6.38, the way that the reaction goes is it starts here at the starting material, and then you go around like this to the final product, like that, okay? So if we look at the first reaction, could anybody tell me what is happening? Which one of the 4 patterns is happening in the first reaction where I have that question mark? Is that a nucleophilic attack, proton transfer, loss of leaving group, or rearrangement? Where I have that red question mark. Yeah, exactly. Thanks, Rubio. It's a proton transfer. Exactly. So let's draw that. Going to look something like this. So you can see we're making a bond between the oxygen of the carbonyl. So then we're going to have something that looks like this. Okay. The next step, so this was a nucleophilic attack. In the next step, we're going from here to here. And you can see that we have an electrophilic carbon here, and water is acting as a nucleophile. And it's going to attack that carbon like this. We can't have 5 bonds to carbon, so we have to put a lone pair up here. So this would be a nucleophilic attack. Did I put nucleophilic attack for the first one? Proton transfer. There we go. Okay, the next one is going from here to here. So if we zoom in, you can see we end up removing this proton. And so that means that water is going to have to behave as a base in this case. And it's going to have to remove one of these protons and put the lone pair on here. So this would be a proton transfer. The next step is this one here. You can see that the oxygen of the carbonyl, meaning this one, takes on a proton. So that's pretty obviously that it's a proton transfer. So we take a proton from our hydronium. So this is a proton transfer. Then we have to close up the ring, right? So we go from something that is linear to a ring. So how do we make the ring? Well, we have the oxygen of the alcohol, and it could be this one or this one, doesn't matter. But this is going to be a nucleophile, and it's going to attack here. Then if you count the number of carbons, look, or atoms, 1, 2, 3, 4, 5, 6. So there's your 6-membered ring, right? 1, 2, 3, 4, 5, 6. And so you form your ring like this. And then the last step is going to be another proton transfer where the water is going to act as a base. So this was a nucleophilic attack. And the water is going to pick up this proton, put your lone pair down on here, and then you end up with the cyclic molecule at the end. So we have proton transfer, nucleophilic attack, proton transfer, nucleophilic attack, and the last one is a proton transfer. All right, there you go. So what we'll do on Tuesday morning, so we're going to save this one for, then. Some of these are kind of tough. This one's okay, but I think one of these, it might be this one here, is like one of the challenge problems. So it's kind of a tough problem, but we can take a quick peek at it. Anyhow, but this will kind of get us going on the idea of drawing our curved arrows.